So we've got a lot of words here. We've got a model of the motion of an international space station. It's traveling at a speed of 27,600 kilometers per hour in a circular orbit at about an altitude of 400 kilometers. The radius of the Earth is approximately 6,400 kilometers. Does this turn you off like right away? Yeah, or you're just like, oh, I can't wait to get into this question. It says visualize. If it says visualize, it probably says draw a picture of this. So we're going to let's make our globe here. Should we include some countries? Oh man. There we go. Here's Africa, part of it. Oh, we should just draw maps for the rest of class. Make the boot. There we go.
Where's Australia?
Australia's part of it's over here.
Australia's in the middle of the
Okay, Greenland. There we go. A little bit of Antarctica.
Did you forget Canada?
Oh, Canada's right here. Right.
It's pretty good though. Mine is scribbling. Big triangle.
Okay, there we are. And we've got a space station. How should we draw a space station?
Up there.
Oh, should it have some like sort of wings on it or something?
That's the satellite.
Ooh, it looks like an angry professor. Okay, there's our space station. And if you went from the center of the Earth, so I'm going to draw a red molten lava thing there, and this part would be 6,400 kilometers, and then your space station is another 400 kilometers, and it's traveling in a circular orbit around the Earth. Does that make a visual for what's happening? Okay. Now it's traveling pretty fast. It's going at 27,600 kilometers per hour. I'd like to know what that feels like. You wouldn't? Have you ever been on a plane and like have to walk to the washroom? Have you ever imagined how fast you're walking at that point? 'Cause you're like going super fast. Okay. So now we've got this. We want to know in 40 minutes, this is going to be somewhere along this. So we don't know how far, but in 40 minutes, maybe it gets this far. Okay, to the nearest tenth of a radian, through which angle will it have rotated? So it has rotated this much. What would that angle be?
You guys changed to 7,600 minutes.
Yeah, we're going to have to do a little bit of changing here. So we're trying to find this angle, and what are the things that we know? Well, we know the radius is 6,800. Do we know the arc length, or could we figure that out? How far has it gone? We can, because we know how fast it's going, and we know how long it's gone. So if I want to figure out this value here, it's traveling 27,600 kilometers per hour, but it's only traveled that for 40 minutes. We can't just multiply this by 40, because this is in kilometers per hour, and our time's in 40. What number should I use? 40 out of 60. Because that would be what percentage of an hour we've gone, or 2/3. So we take our calculators out and we do that number. So I'm going to call this S equals, because that's our arc length, 18,400. So this distance along here is 18,400 kilometers. All of our units are in kilometers. So this is our information that we have so far. This is an arc length question. Arc length questions are when you have something to do with arc length and something to do with an angle. With radians, our arc length formula, which is on our formula sheet, is S equals theta r. What do we all know? What are we trying to find? We want to find theta. We know the arc length is 18,400. We don't know theta, but we know the radius of the space station is 6,800 because it's the 6,400 plus the 400. You could still do this in degrees, but then you'd have to use your degree formula, theta out of 360, and then figure out what proportion of the whole circumference. But radians say that however many radiuses you travel along here, along the outside edge, that's going to be your angle. So if the radius is 6,800, can you see that we've traveled one 6,800, another 6,800, and not quite a third one? So when we figure this out by dividing both sides by 6,800, (2.7 to the nearest tenth). Again, change your equal signs into approximation signs. So our angle is approximately 2.7 radians. How good was my diagram?
It was beautiful, like magnificent.
How accurate was my 18,400?
Wow.
Because if it's supposed to be 2.7, where should it have ended up more realistically? Let's closer to it should have gone about there maybe? Because halfway around would be how many radians? 180 degrees would be 1 pi. Right, 180 degrees is pi radians, and pi is 3.14. We're traveling 2.7. So this is a more reasonable answer. Part B. What is the straight line distance between the initials here? So let's say the space station's like, I want to save some time. I don't want to go around in this orbit. I'm going to go straight through the Earth. We've got a drilling thing on the end. Right through, straight across, and end over there. Perfect. Okay? That would be really, you make a tunnel from Vancouver all the way to Australia. It'd be really good. So how far is that? So now I want to find that black line. I'm going to redraw things here because what happens in a question like this is it got busy up there. There's a lot of things happening. We want to find this black line. We have to deconstruct what we have there and say, do I have enough information to put this into a form that I've used before and forgotten, maybe? That black line, if I redraw the center of the Earth right there with two purple lines coming from it, can you see that triangle on that original diagram? What do we know about this triangle? The purple parts were radiuses, so they're both 6,800. This angle is 2.7 radians. How did you solve that kind of triangle in grade 11? Can you use SOHCAHTOA? No, can't use SOHCAHTOA. You have to use the sine law and cosine law. In particular, this one would be cosine law. Use the sine law when you have an angle and its opposite side. In this case, the angle that we have, we don't have the opposite side. Now, the cosine law is not on your formula sheet this year. So that means they expect you to know it. Do they really expect you to know it? No. I don't think you'll get, never seen a question with the cosine law on your final exam. Okay? Do they expect you to know it next year on your IB exam? Yes. That's why we're doing this question. So a reminder of what the cosine law is. Whatever side you're finding, so in this case, it's x, that will be on the left side of your equation. X squared will equal the other side squared plus the other side squared minus 2 times those other sides. Oh, I'm running out of room. I'll just put a dot there and continue it here. Cos of 2.7. I'll write out the formula again for you. A squared b squared plus c squared minus 2bc cos A. The key in this formula is whatever side is here corresponds to the angle there. The other two sides, B and C, really doesn't matter which order they are or what they are, as long as in the cosine law, the opposite side and the angle go together. Sort of a theme in both the cosine law and the sine law. So now in this case, you have all of this information here on the right-hand side. I want you to start getting used to using your calculator completely and fully that way. So first of all, I'm going to get the number that we had before. 18,400 was divided by 6,800 to get 2.7. That was probably the last thing you have in your calculator. Now, I'm going to go to the equation here. I'm going to write the right-hand side. So 6,800 squared plus 6,800 squared minus 2 times 6,800 times 6,800. The calculator is very smart. When you put brackets there, it knows that you're multiplying. Multiplied by cos. Now, if I wrote 2.7, I would be rounding early because I'm using a rounded value before I figure out my final answer. So we don't want to use rounded values early. We only want to round at the end. So even though we wrote 2.7 here, we want to use all of those decimal places in this answer. To do that, you'd either have to retype them all, or most calculators have something built in where you can go second, in this case, answer, and it pulls your answer from the previous one. Once I do this and I push enter, I get a very large number. Yes? What we're not going to be considered about significant figures as we go through. What we're going to do is we're going to just round in the end. So in science and stuff, you have to consider how many significant figures you've had all the way along, and that affects your final answer. We will do some of that in the IB course next year, looking at significant figures, and it's going to be a tiny bit different than science, but basically the same. But in this case, you get this big number. What's that equal to? That's going to be what x squared is equal to. So x squared was equal to, oh my goodness, such a big number. Just drag your calculator screen somewhere and put it on here so you don't have to. Can you do that on your notes? Just drag your screen? Perfect. 1,763,19638.5. Well, it actually goes further than that. What do we need to do to that to find x? We have to square root it. Second, square root of our answer, second answer. Again, very nice that you don't have to retype everything. And so x is equal to approximately 13,278. It said round to the nearest 100 kilometers. So the nearest 100 kilometers would be 13,300. If a word problem has units, you need to include units as well. So this was in kilometers. We need to write kilometers in our final answer. What's that? You square rooted it twice. 278, now I have 269. All right, I'll see what might be different. Oh, you used the 2.7, and I used all the decimal places, 2.70322. So that's where the rounding early affected your answer a little bit. Okay, questions 8 and 9, and we'll take a little bit of time now to work on those.